You are on live.
So thank you very much for the second talk of this afternoon session of the COPAC Conference on Parallel Computing. I'm happy to have our fellow countryman Yehuda Ben from Ben-Gurion University from the Physics, Chemistry, and Electro-Optic Division. And he will talk about quantum rotors, magnetometers, accelerators, and rotation sensors. So thanks, Yehuda. You will start. Please ask question on the chat. I will see it on the chat and favorite and will ask Yehuda. And Yehuda, please be on time since we are restricted by the other rooms and other seminars. So thanks, Yehuda.
Thank you, Yossi, and thanks to the organizers for inviting me to this conference. I want to tell you a little bit about how to make quantum rotors. Quantum rotors are basically systems that have a disk-shaped density of states. That is, atoms go around a center of a potential. And these quantum rotors can be used to make sensors. They can be used for magnetometers, for accelerometers, and for rotation sensors. The quantum rotors that we're going to use are going to be atoms. They're atoms that are caught in a potential. The first application that I'm going to tell you about, and the one which I will concentrate on, are atoms in a spin-dependent optical lattice potential. So the atoms are trapped in this optical potential and they go around the minimum of a potential, and they are elementary quantum rotors. If you look at the web page for quantum rotor models, you will see the Wikipedia page says that there is no experimental way of making an elementary quantum rotor, but in fact there is. And I'm going to tell you about several different ways to do so. So I'm going to develop the theory of atomic quantum rotors. I'm going to show you their wave functions, their energies, their degeneracies. I'm going to tell you that you can do this with bosonic atoms and fermionic atoms, that these atoms in the optical potential, these quantum rotors, can be used as sensors, extremely high accuracy sensors. So you see that there are two physical review letters that were published recently on this subject. Let me just show you what the density of the quantum rotor wave function, that is, the atom has a density as a function of position, that is shown over here. So there are some atoms that are going around one way and other atoms that are going around the other way, and these states are degenerate. Another way of making a quantum rotor wave function is to take atoms and put them into a retroreflected Laguerre Gaussian beam. So this shows light on the form of a Laguerre Gaussian beam coming in from the left. There are two lenses which make for a plane wave front. There's a back mirror which retro reflects the beam, and the potential that the atoms see is shown over here. So this is the potential as a function of x and y. The z direction is taken to be along the beam axis, and x and y are the coordinates perpendicular to the beam axis. And you see that the potential is very high in the middle. It drops to a minimum and then comes back up. So the atoms like to be in the region where the potential is very low. We will then solve the Hamiltonian for the energy eigenvalues and eigenfunctions. And these atoms can also be used high accuracy rotation sensors and high accuracy acceleration. So let me first begin and say that there are magnetometers in our phone, right? Magnetometer is a device which measures magnetic fields. Typically in our phone, there's a Hall effect that's used to measure magnetic fields. In the case that I will be talking about, the sensors will be measured. The sensors will be atoms that are in these optical potentials, spin-dependent optical lattice potentials, and we're going to measure the amount of magnetic field by looking at the splitting of a degenerate state, and that splitting is going to be directly proportional to the magnetic field. And of course, since we can measure energy levels to the highest precision possible, this can be a very high precision magnetometer. These atoms can also be used as a rotation sensor. Typically, rotation sensors are in a plane, for example, are made from an optical gyroscope, light going around a fiber optic in two ways, and the interference pattern is affected by the rotation. In our case, again, the rotation of the whole coordinate system will be determined by a splitting of degenerate levels, and therefore the rotation can be measured to very high accuracy. Also, accelerometers are present in our telephones, in our cellular phones, and of course they're used for gaming, but they're also used for many other things, such as to monitor vibrations and inertial guidance systems. And the atoms in these optical potentials can be used as accelerometers as well. So how do you make an optical lattice potential which is spin dependent? Well, in this particular configuration that I have over here, we have 6 beams, basically 3 retroreflected beams, but each one of the beams has 2 polarizations, epsilon 1 and epsilon 2 coming out of the board. And as a result of this configuration, the optical lattice will produce not only a scalar potential, but there will be a vector potential as well. And in fact, for atoms with hyperfine structure larger than 1/2, there will be also a tensor component to the optical lattice potential. So I take these 6 beams with polarizations that have 2 components, a Z component out of the board, out of the plane of this figure, and a components in plane. And that produces an optical lattice potential which couples directly to the spin of the atoms. If we take a look at the electric field that results from such a configuration, we see that there's a component of the electromagnetic field in the Z direction, and there is an in-plane component as well, which has this rotation behavior over here. Now, what happens when you put an atom into an optical lattice? Suppose I have 2 counter-propagating beams over here that are coherent. It will make a standing wave pattern. Now, these atomic levels over here, this is the ground state of an atom, and this is an excited state of the atom. If the light frequency is a little bit red-tuned from the transition, what will happen is that the ground state will be shifted down in energy. So the atom will want to sit where the light intensity is the highest. And this particular configuration that I have over here has only one polarization. But if there's more than one polarization, then we can make a potential which is not only a scalar potential, but also has higher a vector component, which couples to the spin. And for atoms with larger than the hyperfine value of 1/2, even a tensor component. So these optical potentials were used to make Bose-Einstein condensate interference problems patterns. And as we, imagine that we have light beams coming in a plane, then the pattern that one will make looks like this. This has been experimentally observed, and it results from the optical potential that the atoms feel. I'm going to be interested in cases where there's only one atom per latticite, because I want to make sensors and I don't want atoms to collide. I don't want a collision event which can change the spin of the atoms. So we know how to load atoms into an optical potential in such a fashion so that only one atom sits in a latticite. This is very important for making a sensor. We can, of course, have a configuration where many atoms sit in each latticite, but then collisions have the possibility of changing the spin states, and this will degrade sensor capability. What is the interaction of the light with the atom? Well, it's the light-atom interaction is just given by the scalar product of the electric field with the electric transition dipole moment of the atom. If we do second-order perturbation theory, we obtain the second-order AC Stark shift, which is proportional to the intensity of the light field, inversely proportional to the detuning, and with a matrix element that goes between the state of interest A and intermediate states, and then we sum over intermediate states. When we work out what this second order Stark shift is, we see that there will be a scalar term. So this is the ordinary polarizability, AC polarizability of the atom. But if we have interesting polarization components, then we can have a vector part, and we can even have a tensor part. However, we're going to be interested in atoms with angular momentum with hyperfine equal 1/2, and in that case, the tensor component will vanish identically, and we will only have the scalar part and the vector part of the potential of the AC Stark shift present because of symmetry. So the full potential will be composed of a scalar part and a part that couples directly to the spin of the atom, where here we're taking J to be the total angular momentum of the atoms and I to be the nuclear angular momentum. So the sum of the electronic and nuclear angular momentum gives us the hyperfine quantum number F, and the light field couples directly to F when the angular momentum of the atom is 1/2. There will not be a tensor term. There will only be a scalar term, which is proportional to the intensity, and a vector term for the case of atoms with J equals 1/2. The potential for the configuration that I showed you with these 6 beams is almost cylindrically symmetric, but in fact it has hexagonal symmetry. Right near the center of the cell, it's very much optically isotropic, but in fact there's a hexagonal symmetry if we go out further away from the center. And the effective magnetic field, the magnetic field that this fictitious magnetic field, Claude Cohen-Taniguchi called this coefficient that couples to the spin of the atom a fictitious magnetic field. So this fictitious magnetic field will be largely radial. It will be 0 at the center of the cell. It will be in the radial direction, except when we go out far enough, and then the cylindrical symmetry will be broken. We see over here that, in fact, the magnetic field has, other than just radial dependence, for a large, very far away from the center of the cells. So in the isotopic approximation, we know how to determine the scalar potential. It's shown over here. So it's a trapping potential. It's an attractive potential that keeps the atoms near the center of each cell of the optical lattice. And there's a magnetic field which is 0 at the center, grows to a maximum value, and then falls back down to 0 for large enough distances away from the center. We can now, given this optical potential, which has a scalar part and a vector part, we can solve for the motion of the atom in the optical potential. So this is going to be the wave function for the atom, which includes the motion of the atom in the optical potential, as well as the internal states. This wave function has 2 quantum numbers, a principal quantum number and a projection of the total angular momentum of the atom. This term over here in the Schrödinger equation is the kinetic energy, which is written over here in polar coordinates. F sub r is the radial part of the hyperfine quantum number. It's the radial component of the hyperfine F quantum number. And we want to find the energies and the wave functions. And we do so by solving this problem in a certain basis set, where, again, there's a good quantum number zeta, which is the projection of the total angular momentum of the atom on the z-axis. And there's a principal quantum number over here, which gives you the motion for the motion of the atom radially, the radial motion of the atom. So we've solved for the energy eigenvalues for an atom such as lithium-6, which is a fermionic atom and has hyperfine quantum number 1/2. And the spectrum is shown over here. The ground state over here has this quantum number zeta, which is the projection of the total angular momentum, which is given by +1/2 and -1/2. So there are 2 states that are exactly degenerate over here, and that's the ground state. In fact, all of these states are doubly degenerate, as are these higher lying states with larger quantum number zeta, larger total angular momentum, which can be ±3/2 or 5/2 or 7/2, etc. We're going to be interested mostly in this ground state, which is degenerate. But as we put on an external magnetic field, or if this whole system is in a rotating frame, such as the Earth frame, that is, the rotation will then be the rotation due to the rotation of the Earth, or an accelerating frame, then this ground state over here will split. And the splitting will be proportional to either the external magnetic field or the rotation or the acceleration. And we will be able to measure the splitting, and we will measure that splitting through spectroscopy using Raman transitions in a Ramsey fringe method. So this is what the ground state wave function looks like here, which is degenerate. There are two states that are completely degenerate, the state with zeta equals +1/2 and the state with zeta equals -1/2. And the excited radial state will have an additional node in the radial part of the wave function. It will also have this kind of symmetry, but will have an extra node. We're interested mostly in the ground state and the splitting of the ground state due to external fields. So in the presence of a magnetic field, these energies, this is the ground state energy, will split. And we're going to measure this splitting. The splitting is going to be proportional to the external magnetic field. Or in the case of a rotation of the coordinate system, the splitting will be given not by the Zeeman Hamiltonian as we had for the external magnetic field, but by the coupling of the total angular momentum to the rotation of the coordinate system, which will then give us a splitting proportional to the rotation. And we're going to measure that splitting. And that splitting is going to give us the rotation or the magnetic field, the external magnetic field. So this would be the split ground state. We see over here that in the presence of an external magnetic field, the degenerate state is split by a certain amount, and we're going to measure that splitting through a Raman transition and go right on resonance using Ramsey fringe methods to measure that energy splitting. Okay, so let me just conclude by saying that the wave function of an atom trapped in a spin-dependent optical lattice potential is confined in circular orbitals, circular orbits around the minimum of the potential, that for a fermionic atom, the ground state is degenerate, that degenerate state is split either by a magnetic field, an external magnetic field, or an acceleration, or a rotation, and that splitting can be measured to determine the rotation, the acceleration, or the magnetic field for the system. Thank you for your attention. I am now going to stop sharing. So if there are any questions, I'd be glad to entertain them at present.
So thank you for the very nice talk. This is from general remark in the chat. I don't know if you see it. It makes a nice connection to the talk tomorrow, and actually in general to the talk about what we are doing. But since I would say if we have the Earth's magnetic field, so you cannot distinguish between angular momentum and the Earth's magnetic field. It will give you the same splitting.
No, you can actually, by doing several different experiments with different configurations of the optical lattice, you can actually tell the difference between a magnetic field, a rotation, or an acceleration.
So this is angle. of the.
Yeah, so this is actually outlined in the first paper in the 2019 Physical Review A paper, which outlines exactly how to tell the different effects apart.
Oh.
So you can actually tell the difference between an external magnetic field or a rotation and or an acceleration.
Okay, thank you. We have another talk here in the chat. Either from Carlo, from Italy, either a way to use the device at room temperature.
So these energies are very, very small, and the trap depth has to be larger than the temperature, and the trap depth is small. That means that we have to use cold atoms. There are other ways, though, of making quantum rotors. For example,
But I think when you talk about cold atoms, they are cold because they are not moving. The laser themselves, the device, is at room temperature.
No, so first,
cold, yeah.
what you do is you cool the atoms.
Yeah.
You cool them first by, light cooling, that is Doppler cooling of atoms. And then if you need to, you cool further by evaporative cooling. And then you have the cold atoms, and then you gently put on the optical potential. And you want to put on the optical potential in a certain way so that you have only one atom per latticite. Or you can even do this for molecules. We haven't really studied the molecular case, but it is interesting to try to think of molecules in these spin-dependent optical lattice potentials. That's something that we have yet to do. Moreover, you can also put atoms that are charged, ions, in a Paul trap in a certain configuration, which will make them quantum rotors, and you will again have the ability to do to make sensors, but there you can control the size of the device, which is basically the size of the disk that the atoms move in, and you can make it rather large so that you can control the splitting by controlling the nature of the Paul trap.
Okay, this is interesting. Actually, chiral molecules, if you can put amino acids, it will be very nice, but this is probably harder.
Yeah, well, I think we're going to try diatomic molecules first.
Yeah. Okay, so thank you very much for the very nice and interesting talk. We have, again, a 10-minute break, and we'll go to the poster session room. Any other questions? Okay, so thanks.
Thank you.
Okay.